So this is the second of our sessions on how do we do proofs, and it's the third of the special sessions on proof. And today we're going to be looking more at developing a bit of theory and using results that you've previously established or know from last year, and standard tests and things like that, to help you get a little bit further. A bit of notation to start with. To do with sequences, the sequences today will be always starting from k equals 1 when it's a sequence xk. So there'll be sequences x1, x2, x3. The first term will always be x1. Of course, you can call it xn if you want. It doesn't have to be xk. It doesn't really matter what we call the w variable. And today we're going to be talking a lot about strictly increasing sequences. So since our sequences start with first term x1, a sequence of real numbers is strictly increasing if x1 is strictly less than x2, strictly less than x3, and so on. Each term is strictly bigger than the previous one. Now, not everyone agrees as to whether 0 is a natural number. It's rather important today that 0 isn't a natural number for us, so our natural numbers start from 1. And that affects the answer to the next question. So in fact, the next question's got two different answers depending on your definition of the natural numbers. We'll work with our definition today, where the natural numbers start from 1. And here's your first question to think about. It's not a trick question, it is an easy question, as long as you understand what the question is asking. And what's the question asking? Well, it says, all you know is you've got some strictly increasing sequence of natural numbers. And you're asked to think about all the different possible values that n2 might have. What's the smallest one? Can you actually get that? What's the smallest possible value you could get for n200? And in general, for a given k, what's the smallest possible value you could get for n sub k, where the n2 and the n200 were special cases? So the answer is not, as some people have said in the past, 1, because you know it's a natural number. But in fact, as k varies, the answer will vary, because the further along you go, the bigger the value of nk has to be. So you should get an answer that depends on k. You don't have to give a formal justification. But if you did have to justify it formally, you should think about what proof you would use, what proof structure. And if you do all that, then you can think about how does the answer change if you use the alternative definition of the natural numbers. So what we'll do is we'll pause the recording there and see how you get on with that question, and we'll get feedback quite soon. So I think most of you have made good progress on that, and of course, the way to think of it is the first term has to be at least 1, because it's a natural number, and the second term has to be bigger than the first term, but still an integer, so it's got to be at least 2. The third term has to be at least 3, from which you quickly see that the 200th term has to be at least 200, and more generally, the kth term has to be at least k. I'll just write down something about that. So this is the first bit. So this is question 1. And we're given nk, a sequence of natural numbers, and n1 smaller than n2 smaller than n3, and so on. Then n1 is greater or equal to 1, because it's a natural number. So n2 is greater than 1, giving n2 is greater or equal to 2. So n3 is greater or equal to 3, and so on. n200 is at least 200. And nk is greater or equal to k, whatever natural number k you take. That's not quite the end of the story, though, because you want to be sure that you actually can achieve this minimum. So clearly the minimum value possible for nk is k, or is greater or equal to k. But you can achieve k using the sequence that goes 1, 2, 3, 4, and so on, i.e. nk equals k. Or in other words, if you take nk equals k, then you manage to achieve nk equals k. But you have to think about the fact that I'm using nk equals k for two different reasons in that sentence. So this shows that the minimum value possible for nk is k. Now, if you work with the other definition of the natural numbers with naught in it, then all the numbers go down by 1, because n1 could be 0, and so on. And if you did want to prove this formally, and I'm not asking you to, because I think that you can say this is clear, you could say clearly nk is greater or equal to k in this setting, and then move on from there and use that fact. But if you were asked to give a formal proof of it, which method of proof would you use? Any suggestions? Proof by induction, exactly. So you can prove this by an easy proof by induction. So you can prove nk greater or equal to k by an easy induction. And I won't ask you to, but as an exercise you can check the details. The nice thing about year 2 is that you could often say an easy induction shows, where in year 1 you're actually asked to do the horrible induction. So you can get away with a bit more in second year, but if you're not sure you could write the proof by induction out, then that's a suggestion that suggests that you should, because it's worth making sure that you are happy with proof by induction. Right. So let's go back to the main presentation. Now, that fact we just established will be useful later. In question 2 and question 3, that result, elements of that result will be relevant. So I'm now going to give you the remaining 2 questions, but we're going to be discussing them. We're going to be discussing the questions rather than just simply try to do the questions. Because I want you to start to think about how you do proofs. And so when you see a question, I want you to start thinking, what does that question mean? What are we being asked to establish? And things like that. So there's going to be questions about questions, and I call those meta-questions. I won't ask you questions about the meta-questions, because then there'll be too many metas going. And we're going to build on what we just said, and we're going to use facts from last year. Looks like there are still a few of those handouts left. Or maybe not. Have all the handouts gone? Gosh. Okay, there's a revision sheet with standard results from last year on standard convergent series. So I believe most of you have got a copy of that sheet. Otherwise, you may have to share. So those standard series will be useful in these questions. So it's worth knowing them. You don't have to prove the results about those standard series. You're allowed to quote results about standard series from last year. You're also allowed to quote and use the comparison test or any of the other standard series tests from last year, which I hope you've brushed up on before this session. And I remind you again that naught is not one of our natural numbers. So question 2 says, prove that for every strictly increasing sequence of natural numbers, nk, that this series, the sum of 1 over the square of nk, is a convergent series. And question 3 says, is it always true for every strictly increasing sequence of natural numbers nk that the series, the sum from k equals 1 to infinity of 1 over nk, without squaring it, is convergent? Now, before you go ahead and actually do those questions, here's question 2 again, and here's some questions about question 2. It asks you to prove something for every strictly increasing sequence. So perhaps you want to think about what it means you've got to establish. You might want to reformulate the statement of question 2 into another form where it's easier to know what the first line of the answer is going to be. What should your first genuine line of the answer be? You may well want to quote some standard facts, definitions, and so on as well. But once you've established the standard definitions and facts that you're going to use, what's the first sort of genuine line of the proof going to be? And then, yes, what sort of things are you going to be assuming, using, proving in your proof? And I've already mentioned that the results we used earlier might be relevant here. And it's also likely that facts about series from last year will be important, and including the comparison test, and standard convergent or divergent series may turn up. So I'll pause the recording there to let you think about what this question means and what you have to do. And we'll let you have a think about that, get a little bit of feedback on that, then I'll let you have a go at actually doing the proof, and then we'll finish off the session by having a look at question 3 as well. So let's see, let's pause the recording there. So with this question 2 then, you're going to be allowed, the idea is that you're going to be allowed to assume you've got some strictly increasing sequence of natural numbers, nk, and from that assumption, you need to be able to prove that the sum of 1 over nk squared is convergent. So you should only assume that nk is a strictly increasing sequence. And if you can then make deductions from that, which give this result, that the sum of the 1 over nk squared is convergent, then you'll have proved it for all sequences, all strictly increasing sequences nk. So the way to think about that is there's lots of different ways of formulating it, like you could say, if nk is a strictly increasing sequence, then that series converges, or suppose that nk is a strictly increasing sequence, then that series should be convergent, or let nk be a strictly increasing sequence of natural numbers, and then deduce that that's convergent. So all these things incorporate the same elements. So reformulating question 2, here are some of my ideas. You may have had other ways to do it as well. You can have things like, given that nk is strictly increasing, show that the sum from k equals 1 to infinity of 1 over nk squared is convergent. Or you could be asked to prove this statement, let nk be a strictly increasing sequence of natural numbers. Then this series should converge, and you could be asked to prove that, and that would have the same effect. Etc. But whichever you come up with, the idea is that you're going to be allowed to assume that you've got a strictly increasing sequence of natural numbers, and then you're going to make some deductions from that, and you should arrive at the result. So I would recommend the first line let nk be a strictly increasing sequence of natural numbers, or something like this. Or in cases where you're worried about the empty set, which isn't happening here because you know there are some, you could say, suppose that. This is even safer. Suppose that is the safest possible one. Suppose that nk is a strictly increasing sequence of natural numbers. Or some shorthand using symbols, whichever. Start with one of those, make some deductions using facts we proved earlier, using maybe standard series from last year on that handout that I gave you, maybe using the comparison test. Let's see whether you can now prove the whole result. So I'll pause the recording again and see if you can finish it off, starting with there. Right, so let's see how I continue this. So we'll have proof continued. So you've got this strictly increasing sequence of natural numbers. Now what I'd say is, as we saw earlier, or you could just say clearly, nk is greater or equal to k for all k. So 1 over n, well, we've got naught is less or equal to 1 over nk squared is less or equal to 1 over k squared for k a natural number. Now, why would I want to do that? Well, we're looking at a series whose terms are 1 over nk squared, and I want to use a comparison test. So I want to know how big can 1 over nk squared be? And we know that 1 over nk squared is at most 1 over k squared. So in fact, that's a decisive case. But the sum of 1 over k squared is a standard convergent series from last year. So since that's a standard convergent series, and you can quote that, then by the comparison test, the sum with the smaller terms in converges as well. And we finish. So what did I do? I wanted to use a comparison test to help me. I looked for an upper bound on 1 over nk squared, and we had one from earlier, namely 1 over k squared, and that turned out to be a very good upper bound. It was also decisive, because we knew you could actually get 1 over k squared. That was going to be the worst possible case. Fortunately, the sum of 1 over k squared is okay. It is convergent, so the comparison test applies, and the sum of 1 over nk squared converges as well. Any questions about that proof? If not, we'll move on to question 3 to finish. And this time you're asked, is it true that for every strictly increasing sequence of natural numbers, this series, sum of 1 over nk, is convergent? So a few meta questions. Is a question harder when you're not told the answer? I'll give you for free that usually has the answer yes. You normally have to, if you're not sure what the answer is, you often have to, at the same time, try and find a counterexample and try and find a proof. And when you can't find a proof, the obstacle is normally that you find a counterexample. And when you can't find a counterexample, the obstacle to finding the example is usually that there's a proof you can find. And then, of course, there's most of research mathematics where people spend their time trying to figure out what the answer is and are unable to find a counterexample or a proof. You may or may not have a guess as to what the answer might be. If you've got a guess and you can quickly justify it, then you've finished. If you've got a guess and you can't justify it, then your guess might be wrong. But what do you have to do if you want to answer this question? Well, either you've got to find a proof that works for every strictly increasing sequence, nk, or you have to find one counterexample. One counterexample will do it. If you can find a strictly increasing sequence of natural numbers where that series doesn't converge, then you've finished. So let me see, does anybody already know the answer to this question? Does anyone, okay, first of all, promising not to pick on anyone, can I have a show of hands who thinks that they know the answer to this question? Okay, we've got a few. Let's have a vote, in fact. Who thinks that it is true, and again, I promise not to pick on anyone, who thinks that it is true that the series has to always be convergent for every strictly increasing sequence nk? Okay? Not very many. Who thinks that there might be a counterexample if you can find an appropriate sequence? Got quite a few there. Okay? That's good. And now, is there anyone who can tell me a counterexample? Anybody want to tell me an example of a sequence that will work as a counterexample? Yes? Yes, okay. The sum of 1 over k is divergent, so we can take nk to be n sub k will take to be k. Yes, that's right. Okay, so that will do it. If you take nk to be k, which yet again is the decisive case, you're trying to figure out whether this has to always converge. The way to find it is to take the decisive case, the worst possible case. If you take nk to equal to k, that's the worst it could possibly be. If it doesn't diverge then, it never will. But in this case, it does diverge. But since nk equals k is available, that gives you a counterexample. So, for question 3, no, the sum of 1 over nk need not converge. For we can take nk equals k as an example, and then the sum from k equals 1 to infinity of 1 over nk, that's the sum from k equals 1 to infinity of 1 over k is the harmonic series it's a standard divergent series. So that counterexample shows it isn't always true. And how do we find a counterexample? By looking at the extreme case, the one that would actually determine the answer one way or the other. Because if that would have converged, if the worst case scenario gave you a convergent series, then you'd have been able to use a comparison test and you'd have shown it always converged, which is what we did in question 2. But since the worst case available actually gave you a divergent series, we were able to take that as our counterexample. And so in both cases, you went to the extreme case, resolved the situation there, and then used that to get the answer. Any questions about that example? Okay, if not, then we'll pause there. We'll end the session, and please hand in your feedback forms to the box at the front.